welcome back. So in this video, I want to talk about velocity, displacement, and distance, and really just give you some motivation for why we are doing some of the things we do in integral calculus. So differential calculus was all about rates of change and finding the derivative. Now in integral calculus, we are going to be finding lots of areas under curves. So I just want to give you some insight into why we might do that. And this scenario with velocity is going to apply to all sorts of situations where we just know the rate of change. So we might not know that much about the actual phenomenon that's happening, but we do know how it's changing. And so by knowing how it's changing, we can actually get lots of information about the phenomenon itself. And to do that, we're going to be finding areas under curves, and I want to show you why. So let's revisit velocity. We start with position, usually s of t, and this is the position in relation to a starting point at time t. So we give you a time and it tells you where the object is at. Then the velocity is the rate of change of the position over time. So it's the derivative of the position, s prime of t. And we label this as ds dt, the derivative of s with respect to time. So that's just a little overview of those things, and we're going to talk about what happens if you just have the velocity. What can we find out about the position or the change in position? So for an example, let's suppose we have an object traveling at a velocity of 4 meters per second for 5 seconds. What distance did the object travel? So here we don't have any information about the position itself, we just know how fast it was going and for how long. So we could do this just algebraically, but I want to graph this to show you how we might graph the velocity and determine what's going on. So we could put time on the horizontal axis and then velocity on the vertical axis. And we know that for 5 seconds, so from 0 to 5 on the horizontal, we're going 4 meters per second. So that's a 4 on the velocity output. Then the distance for how far the object traveled is going to be in meters. So we can think of going 4 meters per second, that's the rate, times 5 seconds, that's the time. You'll often hear distance equals rate times time. So multiplying those together, I'm getting 20. The seconds are canceling out in our units, and so I'm just left with 20 meters. So we can think of this calculation as an area where the time is on the horizontal and the velocity or the rate of change is on the vertical. So we're actually taking a width of 5 times a height of 4 and multiplying those together to get our 20 meters. So what we're doing is thinking of this calculation of the distance traveled as the area under the velocity curve. Okay, so let's just go over a couple more vocabulary words that we're going to need when specifically talking about velocity. So first off, displacement is the word we use to describe the change in position of an object relative to its starting location. So how far in relation to where it started did the object travel? Then distance is the total amount traveled. So you can imagine if you threw a ball into the air and then caught it, the total distance traveled would be how high you threw it and then how far it had to come back down. But the displacement would be 0 because the object started and ended in your hand. So it didn't go anywhere in relation to where it started as when it finished. So the difference between its end point and its start point is nothing, but it did travel some distance. Or you could imagine some cars driving. I'm drawing a silly little picture of a car here, but let's imagine it goes 40 miles forward and then 30 miles backward. The displacement would be 10, since there are only 10 miles between where it started and where it ended. But the distance traveled would be 70 miles, since it went forward 40 and then backward 30. So just remember that displacement depends on direction, so it depends on the direction of where the object is going, but distance doesn't depend on direction. It just wants to know how far it traveled altogether. Okay, so let's try an example where you can see the difference between displacement and distance. Let's say the velocity of an object is given by the graph below. So let's say the input is minutes and the output is feet per minute, that's the velocity. And let's say that from 0 to 6 minutes, it's going 2 feet per minute, and then from 6 to 9 minutes, it's going -3 feet per minute. So let's find the displacement and the total distance traveled over this first 9 seconds. Okay, so we're going to think of this as the area under the curve, Specifically, we want the area between the velocity curve and the horizontal axis. So I'm going to fill in these areas here, and then we're going to find what their actual values are. So area is length times width when we're looking at a rectangle. So for my first area, I have 6 times 2, that's 12. And for my second area, I have 3 times -3. I'm thinking of this as having a height of -3 since it's below the horizontal axis. So this has an area of -9. The negative velocity corresponds to a negative direction, like going backward, so we want to make sure we account for that in our calculation. Okay, so to find the displacement, I want to sum up these two areas. So 12 is the first area, and I'm going to add it to -9, the second area. And I'm getting 3 feet. So overall, this object went 3 feet. It went forward 12 and then back 9. So it ended up going 3 feet as the displacement. Then to calculate the distance, we actually want to think about all of these as positive. So we want to think of it went 12 feet and then it went 9 feet. It doesn't matter which direction it went. So I'm really adding up the absolute values of these amounts, or you can just think of making sure to make them positive. So I'm doing 12 plus 9, which is 21. So 21 feet is the total distance traveled. Okay, that's it for this example. Thanks so much for watching, and I will talk to you in the next video.